So I've posted that link to the testimonial up in the chat, but it's also up there on Flipgrid. So if you can create a testimonial for this Africando conference, I'd appreciate it. Certainly might help us get some more scholarships. Okay, I've started recording, so I'm going to go ahead and get started with today. I'll review just a little bit what we talked about last time, but now we're getting into understanding our atmosphere and exactly how atmosphere plays a role in climate change, because obviously it's really important. So we'll go here. So we talked about the components of our atmosphere. It's mostly composed of nitrogen, like almost 78% nitrogen, about 21% oxygen, and then 1% argon. And last time I actually gave you guys a quiz to name those components and name those relative percentages, because that's really important to know. Nitrogen is a fairly non-reactive gas. It does react a little bit. Argon is completely unreactive. Oxygen's very reactive, which is why things rust. Oxidation, there's a lot of compounds that are broken down through oxidation. So the atmosphere is active, but at least those three components, those are completely transparent to visible light. And they're also transparent to infrared light, which is going to be really important when we're talking about black body radiation. As we noted before, water vapor can form a fairly significant part of our atmosphere as well, but it depends on where you're at. At the poles, you'll have really low water vapor concentrations, but in tropical areas, much hotter. And water vapor is important because it absorbs in the infrared. It's still transmissible to visible light, so light coming down from the sun will pass right through it. But when it heats our Earth up and our Earth starts to black body radiate in the infrared, that gets absorbed by the water vapor. And it's actually the biggest contributor to any kind of a greenhouse effect in our atmosphere. It's not as important when we talk about human caused climate change, which is why we're going to focus on some of the other gases, CO2, which, we're talking less than 0.05% of the atmosphere is all the rest of these different constituents. And carbon dioxide's at about 410 parts per million in our atmosphere. And that one does act as a greenhouse gas, as does methane and nitrous oxide and ozone and various halogens. So you should know those components. Should know what a greenhouse gas is. We talked about this. Light coming from our sun passes through our atmosphere because it is transparent to visible light. Some light gets reflected off of our surface, like off of things that are white, like snow and ice caps and glaciers. And that contributes to what we call the albedo for our planet, which is at 0.3. About 30% of the light is reflected back off into space in the visible spectrum. But that which isn't reflected off gets absorbed by the Earth, it heats up, and then the Earth will emit as a black body. And we know how to calculate based on the temperatures that we're at, that radiation is going to be in the infrared, which will get absorbed by certain gases in the atmosphere. And as it absorbs energy, that gas heats up, and then it re-radiates as a black body radiator. And that's the key to what it means to be a greenhouse gas. Greenhouse gas is a gas that absorbs in the infrared, and it heats up because of it. And so it's going to re-radiate that energy in the form of infrared because of the temperature that you're out. And it doesn't let the infrared coming from the surface of the planet go out into space, which is how we would cool off. And so we saw that in some of our climate model calculations. And don't forget, there is a flip grid, a peer teaching that you should do that walks us through how to do climate calculation. I think it's with a 1-layer atmosphere. So I'm eager to see those. Please don't forget to go ahead and do those. Now, as we mentioned, CO2 is one of those gases that absorb in the infrared. And we went through all the physics and chemistry behind that, because all atoms, have certain frequencies by which their atoms bend and stretch, kind of bounce around. And those frequencies are what we call those resonant frequencies. And if you hit a molecule at its resonance frequency with radiation at that frequency, it will absorb it. And so for carbon dioxide, you've got all these different modes in which it can bend and stretch. And we found that some of these lead to absorption at certain wavelengths. Now, when it absorbs at those wavelengths, it's absorbing energy. So now the molecule has more energy, so it's going to do those bending and stretches more, and it essentially has more kinetic energy, so it's hotter, which means it will radiate higher in the blackbody range, as well as its temperature has increased. Now, just to compare, you can see water vapor also absorbs heavily throughout the infrared. This is one of the reasons why it's the biggest contributor to the greenhouse effect. But when we get into man-made stuff, we'll see how man-made stuff is kind of the driver of our current changes. I tried to put up a slide so you can see some of the other gases and the wavelengths at which they absorb. And you can see, remember, our visible range goes out to about 0.85, so less than 1. And so for a lot of these, they don't have nearly as much absorption as this carbon dioxide. So from that, so for a good next few lectures, we're going to, since carbon dioxide is so important, we're really going to focus on carbon dioxide, how it gets in the atmosphere, how it's regulated in the atmosphere, and where it goes. And we call these the carbon cycles, okay? These are the processes which regulate how much CO2 is in the atmosphere. And you can think of them in terms of different regimes of interactions. There's an interaction between the land and the atmosphere. There's an interaction between the land, the atmosphere, and the ocean. And then there are interactions between the land, atmosphere, oceans, and the rocks. And it's then we'll talk about, how humans are really kind of driving this increase in carbon dioxide in our atmosphere. Now, last time at the end of the lecture, we started talking about the land-atmosphere interaction. And I had put up this graph of the seasonal cycle of carbon dioxide. And we talked about how in spring and summer in the Northern Hemisphere, CO2 will drop heavily. And that's mostly because that's the time in which plants are growing. So when plants are growing, they're using photosynthesis and they're using up CO2. So that's going to deplete the amount of CO2 that's in the atmosphere. In fall and winter, however, that pretty much comes to a halt. And some of these other processes are going to take up, like respiration. So since it's a biotech course, we should focus in just a little bit on photosynthesis. And, we all know photosynthesis uses light, right, to grow plants, right? But I like to be more specific because the photosynthesis isn't actually the thing that's making the CO2. The photosynthesis is where it's creating the energy or getting the energy to create ATP, which is going to then allow it to fix carbon in the atmosphere. Does everybody get that distinction? So photosynthesis uses the energy of the sunlight to help create these ATP. And it's that ATP that's going to use later to fix carbon. Okay, and that's called the dark reactions. That's where you take carbon dioxide physically out of the air and chemically bond it into substances, which are no longer a gas, and usually in the form of sugars. But usually, a lot of times people lump these things together and they just say, photosynthesis, creates CO2. Technically, it doesn't, but we're getting there. So technically, we divide them into the light dependent and the reactions and the dark reactions, which you don't need light for. It's during the light reaction that the photons are coming down, hitting the chloroplasts, which have these little thylakoid membranes in them. And that's where they need the water. This is where the water comes in. The sunlight is used to split a water molecule and shoot off high energy electrons. And then those high energy electrons are going to be shuttled through this chemical process where they go from higher to lower to lower to lower energy. And in the process, that energy is going to be harvested to make ATP. And so you can make a lot of ATP during the day when the sun is shining on these plants. And it keeps splitting these water molecules. If they didn't have water, they wouldn't be able to make the ATP, which is going to be used for energy. So that's where the water comes in. Once that happens, and you've made ATP, now in another part of the cell, in the stroma, there's something called the Calvin cycle, which is a series of several different enzymes that use the energy of ATP to help grab onto a carbon dioxide molecule and start to chemically bond it to another CO2 molecule, put on hydrogens, etc., using what's available in the cell to make precursors to sugars. This precursor is known as glyceraldehyde 3-phosphate, but if you see here, it's just 3 carbon atoms that's got some oxygen molecules attached, and it's got this phosphate for these enzymes to kind of hold on to it and lead it through this process. And so these glyceraldehyde 3-phosphate molecules are going to be used to build basic sugars like glucose and ribose. That's going to form what we call cellulose, which is the material of the plant. So if you look at, any kind of tree or plant, what it's made out of, whether it be the leaves or the bark of the tree, those are all forms of cellulose, which are just polymers of sugar, usually polymers of glucose. So if you could break them down into their independent components, it would just be like table sugar. But it's connected in such a way that the way these sugars are connected together, we personally don't have any enzymes that will break those linkages. And so we can't eat cellulose. You can't eat a grass or a tree or something like that. But that's what everything's made out of. That's what trees are made out of. So if we look at, a lot of folks will show you the formula for photosynthesis, and it's basically taking carbon dioxide and water, using the energy from the sun, and then to produce these precursors that are going to make sugars. So this is part of what's going to be going into those glyceraldehyde 3-phosphates. And if you notice from our little diagram here, one of the processes of, splitting these water molecules, taking the high energy electrons, is one of the byproducts at the end of the cycle is oxygen. And so one of our products from this chemical reaction is oxygen, and we're thankful for that because that's what allows us to breathe. The oxygen that it's in our atmosphere is all due to photosynthesis. So when the planet first started, we didn't have oxygen in our atmosphere. Our atmosphere had things like ammonia and methane and some carbon dioxide, but mostly no oxygen. The oxygen in our atmosphere came about from billions of years of blue-green algae. That's what we think are one of the first life forms developed in our oceans. And over 1 billion years doing photosynthesis, they had this byproduct of oxygen, which started to go into the atmosphere. And I mentioned that oxygen's pretty chemically reactive, like, it's what causes things to rust. You may not have known this, but way back in the day when our planet first started, before there was oxygen in the atmosphere, our oceans were actually red because we had high concentrations of iron in our oceans. So our oceans were actually red. And it wasn't until there was a high enough concentration of oxygen in the atmosphere did that iron start to oxidize and essentially rust and precipitate out of our oceans. Because normal iron is pretty soluble in water. When you oxidize it, however, it becomes insoluble and it'll just kind of precipitate. And if you've ever gone to any old rock formations where you see, these huge lines of red in the stone, those are all due to iron precipitation when the ocean went from a red ocean to a blue ocean because of the oxidation of the oxygen in our atmosphere. Now, this is totally unrelated to climate change, but I always thought that was neat to know, is that our planet had red oceans, which basically rusted when plants came around. So photosynthesis really has changed our planet. So it's important to know that the CO2 is coming out of the atmosphere in photosynthesis. The energy is coming from sunlight, and that it's used to make the products that will be used to make sugars, like glucose. And that glucose, in turn, will form into cellulose, and that cellulose will start making up the material of the plant. And as photosynthesis continues, the plant gets larger. And one of the examples I like to use in class for this is, think about if you're going to plant a plant and you put it in in a little pot. Put the seed in the pot, you add some water, put it out in the sun, and you wait for it to grow, right? Well, as it starts to grow, you have to keep watering it, and it gets bigger and bigger and bigger. Where is all the mass of the plant coming from? Like, you could get a pretty big plant, right? And often when I ask this question in my undergraduate classes, they'll say, they're getting it from a lot of nutrients in the soil. Well, if that was the case and the plant keeps growing bigger in your pot, you'd continually have to bring it more dirt, right? To put more dirt in the pot so it could grow up, grow larger. But we never do that. All you have to do is add water, because the mass of the plants, that's coming from the gas in the atmosphere. So all the trees you see when you look around, all of those are made from gaseous carbon dioxide, which was done through carbon fixation in the Kelvin cycle of photosynthesis. So photosynthesis created our ATP. That's what's not shown in here. The ATP was then used in the dark reactions in the Kelvin cycle to actually fix the carbon, take in the CO2, and then start producing the sugar molecules to give us finally a wonderful, beautiful tree, hopefully with fruits that we can eat. So all of the mass of these plants comes from CO2 gas and water. And so what photosynthesis ends up becoming is a net transfer of carbon dioxide from the atmosphere to plants on the surface. And so that's what we see here, is it's just being pulled out and you're growing trees and plants. And that happens mostly in the spring and summer. Now, winter and fall, less sunlight, it's colder, plants stop doing that. And so there's no longer that contribution. Now, there's another contributor, which is going in the opposite direction, and that's respiration. So respiration, its formula might look like this. You're taking sugars from a plant, you're taking oxygen from the atmosphere, and essentially consuming it to release energy. And we're using the energy in ATP for our cells. And as a byproduct, we make CO2 in water. So here we're talking about animals, right? These are the animals that eat the plants. They're taking the sugars from the plant. They're breathing in oxygen. Oxygen's really important for respiration. If you just did glycolysis, which is a breakdown of a simple sugar, you'd get about 2 ATP molecule per glucose molecule. If you do aerobic respiration that involves using the mitochondria of your cells, you're able to break it down much further and harness a lot more energy to the tune of making 36 ATP instead of 2, which is a lot, huge amount in terms of a difference. We do, however, need to consume oxygen for this to happen because, again, what's done in these chemical reactions is you're splitting off high energy electrons and they're going down from high to low energy, and in the process they're generating energy and to make the ATP. Eventually at the end, the last step is that electron is transferred to an oxygen molecule or to water molecules, which then turn into oxygen, and that's released in take an oxygen molecule, which is our terminal receptor for those electrons in that process. And that turns it into CO2, and that's released in the atmosphere. And so this is essentially kind of like the reverse reaction. We're taking sugars and oxygen and releasing CO2 in this case. And so this produces what we call the first of our carbon cycles, where we're going from the land biosphere to the atmosphere. From the atmosphere, carbon is being removed through the process of photosynthesis to the plants in the land biosphere, and then the plants are being eaten or dying and decaying and being consumed through the process of respiration, which then releases the CO2 back into the atmosphere. Everybody following along so far? This is probably all review, right? Just to get us up on the same page. So during the spring and summer, we've got photosynthesis. During the fall and winter, we've got respiration. And these two basically form a cycle, which gives us the seasonal cycle of CO2 that we see. Everybody good on that one? Okay. So next I want to chat a little bit about the land, atmosphere, ocean interaction. Okay, so now we're going to bring the oceans into this. And again, we're talking about carbon dioxide. So you need to know a little bit about the properties of carbon dioxide. And the most important of which is that carbon dioxide readily dissolves in water. It's pretty easy to dissolve carbon dioxide in water. It forms what we call carbonic acid, which kind of looks like this. You're really familiar with this as you see it in a ton of carbonated beverages. All the carbonated drinks, Coke, Diet Coke, Pepsi, Sprite, they're basically dissolving CO2 into the water, which is giving it that fizzy, frothy taste to it. And it's also, while that carbon dioxide is being absorbed by the water and dissolving in it, it's doing this chemical reaction where it's making this weak acid called carbonic acid. So since CO2 readily dissolves in water and forms this carbonic acid, that means it rapidly dissolves into the ocean, right? Because the land is in contact with the ocean. And so you're going to see a lot of the CO2, because there's this border between the land and the ocean. The CO2 is going to get absorbed into the ocean and form more of this carbonic acid. Now, this reaction also happens in reverse. So carbonic acid and water will return to carbon dioxide and water molecules at a given rate. And so this reverse reaction we would call degassing. It's basically the gas leaving the water it's dissolved in. And you're familiar with this as well. When you have a soda and you've left it out too long and it starts to go flat, it's because all of the CO2 has left. And so eventually there won't be any more there. And so we have this land atmosphere ocean interaction now where CO2 will come out of the atmosphere, join with the water of the ocean and make this carbonic acid. And then in the reverse of that, carbonic acid will slowly degas. In other words, it'll turn back into carbon dioxide. That carbon dioxide will then degas out of the water and join the atmosphere. If there's less CO2 in the atmosphere, degassing happens faster. If there's more CO2 in the atmosphere, you tend to favor absorbing that CO2 into the water and it's sticking around. And so, and in general, under normal circumstances, these are roughly balanced over a year-long cycle. Because remember, CO2 is going to go up during the spring and summer. It's going to fall, it's going to go down in spring and summer, and then it's going to increase during winter. And so even though there are these seasonal variations over the course of a year, these going into the ocean and coming out of the ocean are relatively balanced. Now, it's also important when we start talking about the ocean that we kind of understand really the ocean isn't all one uniform thing. It can be divided into layers. So we tend to talk about the top layer being the mixed layer. And then below that is the deep ocean. So the mixed layer is about 100 meters from the top. That's going to readily exchange carbon dioxide with the water, and the water releasing the carbon dioxide because that's the interface that's in contact with the atmosphere. And it's heavily mixed. It's mixed by winds. It's mixed by weather events, hurricanes, all of that. Ocean currents will mix them as well. Any kind of surface activity will mix them. And so for the first 100 meters, it's fairly well mixed. Below that is what we call the deep ocean. That's the other 97% of the ocean. The mixed layer is like the top 3%. Bottom layer is this deep ocean. And its exchange is a lot slower. You'll notice that most of the carbon I have listed on here, how much carbon is in our mixed layer. That's around 900 gigatons. And you can see in the deep ocean, we have many more times the amount of carbon. So up to 45,000 gigatons or 45 teratons. That's a lot of carbon that's deep in the ocean. And in addition to the process by which you're making that carbonic acid and that mixing, and that's how you get some of the carbon down into the deep ocean. There's also another route to increase where the deep ocean gets its carbon, and that's just from creatures dying, from fish dying and slowly sinking to the bottom. Well, when they finally sink to the bottom, their process of decay is going to happen over a long period of time, but all their carbon is stored down there. Because again, the back and forth between the mixed layer and the deep ocean is actually quite slow. Stuff will stay in the deep ocean. Carbon will stay in the deep ocean for a long period of time, centuries, before it gets back into the mixed layer. So if you put all these things together at this stage, we've got the land biosphere, this is where we live. And through photosynthesis and respiration, we're taking carbon dioxide out of the atmosphere and putting it back in. And again, this over the millennia, this has been roughly balanced up until now. Okay. Also, when you've got this carbon dioxide in the atmosphere, some of the carbon dioxide in the atmosphere is dissolving into the oceans, into the mixed layer, and in even a slower process, dissolving down into the deep ocean. And the reverse process is happening as well, where the oceans are slowly degassing. Coming up from the mixed layer, we're releasing CO2 back in the atmosphere. And again, all of this has been roughly balanced, for the last several 100 million years. And here I listed the resonance times. So this is how long carbon molecules will last in kind of these zones. So if you were to release a carbon dioxide molecule now into the atmosphere, it would probably stay in the atmosphere for about 4 years before it's cycled somewhere else. If it goes into the land biosphere, if it's trapped by photosynthesis, then it'll probably be on land and part of the biosphere for about 20 years, growing the plant, creatures eating the plant. They take some of that biomass for themselves. Later on, the creature dies and decomposes and releases that. Or maybe the creature's eaten by another creature. So roughly, it would take about 20 years for that same carbon dioxide molecule to get back into the atmosphere. Once it's back in the atmosphere, hang out there for another 4 years till it's trapped by photosynthesis, or it dissolves into the ocean. And there it goes in the mixed layer, and carbon dioxide will probably hang out in the mix, or carbon will probably hang out in the mixed layer for around 5 years before it either degasses back in the atmosphere or then goes into the deep ocean. Now, if it goes into the deep ocean, it's going to be there for a long time, over centuries. On average, for a carbon molecule going in the deep ocean, it'll reside there for about 400 years before it comes back into the mixed layer. Then it'll stay another 5 years in the mixed layer and then back into the atmosphere or back down to the deep ocean, right? Because it's random where these things go. And again, over the last several million years, this has been roughly balanced. Okay. What we'll talk about next time is we're going to talk about the land, atmosphere, ocean, and rock interactions, because it turns out there's actually a high flow of carbon from the rocks into the atmosphere and from the atmosphere into the rocks. We're going to see and this is where humans kind of go off the rails in what they do, because that's where fossil fuels come from. And we're burning fossil fuels really fast. That's upsetting our overall carbon cycling. So any questions on this?
Hello, Prof.
Yes.
I wanted to ask on this carbonic acid. Can the carbon dioxide which goes into the atmosphere, can it combine with water and it forms that acid rain?
Yes. Matter of fact, that's exactly what we're going to see when we talk about the land, atmosphere, ocean, and rocks. So when it rains and the raindrops are falling through the atmosphere, just like the ocean, those raindrops, CO2 is going to dissolve into those raindrops and form a little bit of CO2, right? or carbonic acid. And so when the rain hits the ground, when it hits rocks, a combination of the force of it hitting the rocks and the carbonic acid leads to erosion. And that's where we get limestone deposits from. A lot of limestone deposits are from this interaction of the carbonic acid that's in the rain that helps form the limestone. It's in a lot of different things all over the world. And so that's a main vehicle for taking some of the CO2 out of the atmosphere. And now it's going into the rocks in the form of limestone and other things. So it's, as you can imagine, being in the deep ocean is what we said, about 400 years resonance time. As you can imagine, going into the rocks, the resonance time is much, much, much larger on the scale of geologic time. But no, it's a great question about the acidification of the rain, and that's generally true. So it means as CO2 goes up in the atmosphere, the percentage of carbonic acid in rain is going to go up slightly. Now it's just a weak acid, but it would make it slightly more acidic. Now, when you've heard about acid rain, you know, that has been in the news a lot and has been a problem, often that's coming from sulfur that's in the atmosphere. And that will form sulfuric acid when it dissolves in water and in raindrops. And so you'd be getting a much stronger acid that comes down when you have sulfur deposits. And sulfur can be released in the air from volcanoes and venting, such like that. And so, as well as a lot of human-made pollution, which can cause the rain to be quite acidic and quite damaging. But yes, you are indeed correct. The CO2 does make the rain more acidic. And the easiest way to check that is if you collect a cup of rainwater, you can get a hold of some pH paper and check the pH. It will be slightly acidic because it's absorbing all the stuff in the atmosphere. And the other thing to note is even particulate matter, you know, from pollution that's been released in the atmosphere, you can really look at rain as kind of a washing mechanism. So when it first starts raining and those water droplets are moving through the atmosphere, if you've got little particular particles like dust and other things, they'll get trapped in the raindrops as they're coming down. So the initial first phase of the rain can actually be kind of dirty. It's not as clean as you might think it might be. But the carbonic acid has always been in there, and that's what gives us our limestone deposits and other rock deposit formations that we have, and is really responsible for a lot of erosion over time that we see from rain and precipitation, but a very important component. Any other questions?
Low proof.
Okay, I'll wait. I'll wait till next time to get into the land, atmosphere, ocean, and rock, because then that's going to lead into really the meat of the course of where human change, human-caused climate change is coming from, which is, again, burning those fossil fuels. You know, how did they get there, those fossil fuels, and what does it mean that we're burning them in such large quantities on such a fast scale? So remember, geologic time scales, millions, hundreds of millions of years. So we're doing things a lot faster. Okay. Thanks, everyone. I appreciate your time. I'm going to go ahead. I see a few of you have done some Flipgrids that I need to respond to. I'm going to go ahead and respond to those. And I look forward to your next ones. Okay. Have a good day.
Thank you.